Well, in this video, I'm going to show you how we describe the electric field due to a very large flat sheet of charge. We often call it a charged plane. Now, this is the geometry version of the word plane. So a large flat area, you might think of like if we were to take the floor, for example, and paint a bunch of charge on the floor, how would we describe the electric field associated with that charge? Now, you're still probably early into your study of electric fields. Just keep in mind what that means. Every charge has an electric field associated with it. It's kind of how we describe what that charge is able to do when we get very, very far away. So we say that the electric field does not exist just at the point of the charge. The electric field exists everywhere around that charge. So you could talk about a point charge. You could talk about a couple of charges together. Now what we're talking about is a large sheet of charge. So first thing you have to know is how we describe how much charge is on a sheet. We actually use what's called the surface charge density. And just kind of what the name implies, it's not how much charge, but how much charge is on a particular amount of area. So what I did here is I imagined a really large sheet, and I've just kind of drawn a little section of it here. And I've shown a handful of charges, but I don't want you to think that those are the only charges there. Again, imagine we have charge that's almost like a liquid that we could paint on. And every bit of the area gets coated with this charge. So we describe how much charge is on, let's say, a square meter of it. And we use the symbol in Dr. Knight's text. This is a Greek letter eta, E-T-A, eta. And in other textbooks, you'll see this written as the Greek letter sigma. So just be familiar with what symbol your particular text is using. And here again is what we mean. This is the charge per unit of area. So let's say so many coulombs per square meter. Well, if we know what that number is, then we can figure out what the electric field is anywhere around this sheet. Now, you can't get too close to the edge of the sheet. This equation I'm going to show you does not work when you get near the edges. But remember here, my picture is not meant to show just a small little plane. It's actually just a small segment of the whole plane. And so that'll suffice for what we're doing here. So here's how we describe the electric field. And this is a pretty surprising result. So if we know that number eta, I know it looks like an N. I'm sorry about that. This is the Greek letter eta. We divide that by 2 times the permittivity constant, epsilon sub naught. You'll see that in just about every expression for electric field. It just describes a property of the air or the material around the sheet. That is how you calculate how strong the electric field is. Now that'll give you the magnitude, how big it is, how many newtons per coulomb it is. But if you want to know the direction, I think it helps just to look at the figure here. Because I've imagined painting this with a positive charge, my electric field lines radiate away from the plane, and in particular perpendicular to the plane itself. Everywhere perpendicular. And the same is true down here, except it's downward because it's radially away. If this were negatively charged, then everything would be toward. So all I'd have to do is draw little arrowheads that point towards the plane. So what's surprising about this? Well, an important thing to remember about field lines is, based on how spread out they are, that determines how strong the field is. Well, notice that no matter where we go, because they're all parallel with each other, the field lines are the same distance apart from each other. That means the electric field must be uniform everywhere. That's the word that we use, uniform everywhere. That means if we take an electric fieldometer and we go anywhere around this, obviously not, inside the sheet, but anywhere around the sheet, again, keep far away from any edges, we always get the exact same field strength. Now that's kind of a shocking result, because I would think most would naively assume that if you're really close to this charged sheet, that you're going to get a really strong electric field. And the farther away you go, the weaker it should get. I mean, after all, that's how it works for point charges and, gosh, just about every other charge arrangement you can think of. So why are sheets different? Well, I would have to use vector calculus, sometimes called multivariable calculus, to actually derive this expression. And that's a fun thing. Once you learn that, maybe in college, you'll be able to derive this expression yourself. Let me give you a little hand-waving argument for why the field is the same. So what I've done here is I've imagined a couple places. Here's a dot right here I drew in green, and it's kind of close to the sheet itself. And here's a dot that's kind of far away. Why would the field here and here be the same? Well, notice that in order to describe the electric field at that dot, I need to describe the little field created by every single bit of charge around here. And I'm not just talking about the 10 charges that I drew. This is more like a paint, remember. So if I were to draw that, each little charge is kind of close to this dot. And so each one would create, I'll call it sometimes like a little fieldlet. And they're all pointed radially away. Now, it's really hard on this two-dimensional paper to show what this is. These are little fields that are all kind of going up and away from this sheet. They all have a little upward component, but they also have a pretty big outward component, if you want to call it that. Something that's kind of parallel to the plane. Whereas up here, because this is farther away from these charges, they're all a little bit smaller. But notice there's more of an upward component to them. Again, I'm not going to be able to draw this very well. But these, because they're farther away, are also more pointed up. So imagine what happens when we add up the sum total of all of these little field vectors to get the total. I have a whole bunch of small ones here, but they are more in line with each other, more parallel with each other in the upward direction. Down here where I'm close, I have bigger field vectors to add together, but they're much more away or pushing away from each other. Pushing away is not the best phrase to use there, but directed away from each other, and therefore they cancel more. They cancel out more. So you'll get a lot more left and right component that cancels out. So what that means is it's possible to get just as much net field here as we have here because of those two competing factors. Smaller fieldlets that are more added together, and here larger fieldlets that more cancel out. And that is exactly what happens, and I can demonstrate then that this field ends up being the same everywhere. So again, that'll have to suffice for now, but just be familiar with this expression here. And I will tell you that once you learn Gauss's law, this equation is actually pretty easy to figure out. Gauss's law is a topic for another time. You have to know a little bit more before we get into that. So we'll leave it at this, and hopefully that gets you through anything you'd have to do with large sheets of charge at this point. Thanks for watching.